The push operation adds an element to the top of the stack, and the append operation adds an element to the bottom of the stack. But sometimes we also want to insert a value in between elements. For example, consider the following stack, 5, 6, 8. Suppose that we want to add 7 in between 6 and 8. The result we want is the stack 5, 6, 7, 8. We inserted 7 at index 2. The elements at index greater than 2 have been moved to the right to make room for the new value. The insert operation is very similar to the append operation. They both pop elements from the stack, push the new value, and restore the popped elements. But rather than popping the entire stack, we only pop until we get to the index we want. Here's a demonstration. Here is the sequence of actions. First we pop 5, then we pop 6, then we push the new element 7, we push 6 back into the stack, and finally we push 5 back into the stack. The result of inserting value 7 to stack 5, 6, 8 at index 2 is stack 5, 6, 7, 8. Since we need to stop popping at index 2, we cannot simply dump the whole stack. Instead, we decrease the index by 1 every time we pop an element from the stack. When the index reaches 0, we stop popping. After the new value is pushed, we can dump the pop stack back into the original stack as before. Let's now try to precisely describe the insert operation. We need to keep track of the popped elements, so we first convert the insert operation to the insert element compute function, whose input is the stack, index, the new value, and the popped element stack. We can convert the insert operation as follows. The result of inserting value v to stack s at index I is equal to the output of function insert element compute, where input stack is s, index is I, value is v, and the pop stack is an empty stack. We can describe the behavior of the insert element compute function in two properties. Output of function insert element compute, where input stack is a, remainder, index is I, value is v, and the pop stack is ps, is equal to the output of the function insert element compute, where input stack is remainder, index is I minus 1, value is v, and the pop stack is a ps. Property 2 says that the output of function insert element compute, where input stack is s, index is 0, value is v, and pop stack is ps, is equal to the result of dumping stack v ps to stack s. Property 1 says that the output of the insert element compute function will stay the same, even if we move an element from the stack to the pop stack, as long as we also decrement the index. For example, let a equal to 3, remainder equal to stack 4, 5, I equal to 1, v equal to 9, and ps to the empty stack. Then, the output of the function insert element compute, where input stack is 3, 4, 5, index is 1, value is 9, and the pop stack is empty, is equal to the same function, where the input stack is 4, 5, index is 1 minus 1, or 0, value is still 9, and the pop stack is the stack 3. The expressions on both sides of the equal sign are equal to the stack 3, 9, 4, 5. So the equation is true. Property 2 says that when the index is 0, then we can obtain the output by pushing V to the pop stack and dumping this stack to the original stack. For example, the output of the function insert_element_compute, where input stack is 4, 5, index is 1 minus 1, value is 9, and the pop stack is 3, is equal to the result of dumping stack 9, 3 to stack 4, 5. Again, the expressions on both sides of the equal sign are equal to the stack 3, 9, 4, 5. As another example, let's evaluate the result of inserting value 13 to stack 11, 19, 17 at index 1. First, we use the conversion property to conclude that the result of inserting value 13 to stack 11, 19, 17 at index 1 is equal to the output of the function insert_element_compute, where the input stack is 11, 19, 17, index is 1, value is 13, and the pop stack is empty. Next, we use property 1 to claim that the output of this function, where the input stack is 11, 19, 17, index is 1, value is 13, and the pop stack is empty, is equal to the output of the same function, where the input stack is 19, 17, index is 1 minus 1, value is still 13, and the pop stack is stack 11. Since 1 minus 1 is 0, we can substitute 0 into 1 minus 1. Since index is 0, we can use property 2 to claim that the output of the insert_element_compute function, where the input stack is 19, 17, index is 0, value is 13, and pop stack is 11, is equal to the result of dumping stack 13, 11 to stack 19, 17. Note that 13 was pushed into 11 before the pop stack is dumped to 19, 17. We also claim that the result of dumping stack 13, 11 to stack 19, 17 is equal to the stack 11, 13, 19, 17. Now we can use the transitive property a few times to conclude that the result of inserting 13 to stack 11, 19, 17 at index 1 is equal to the stack 11, 13, 19, 17.